Hello, I'm Roman, and welcome back to the series of the videos Neural Networks from Scratch in Golang, where we dive into the bare bones of what is the neural network is, and we're trying to implement everything, like all of the layers, input, output, training, using these neural networks from Scratch in Python book, but again, I'm writing things purely in the Golang. And in the previous video, I started to dive into, started to remembering what is the derivative, what's the difference between numerical and analytical, and we checked what is the derivative itself, what is the partial derivative, well, not the partial derivative, what is the numeric derivative and how it's calculated. And today we will start from analytical derivative. So we'll see what's the difference between them and how we're going to use probably both of them. I'm not sure if I will write some code today. Maybe yes, maybe no. We'll see. But in order to play around with the functions, I launched the Jupyter notebook where we can easily plot things, because I'm not sure that I will need this. I'm not sure that I will need the code from this chapter later, so I think I will just stick with the Python for the diving into the derivatives. Also, have you been in the situation where you change your apartment or the house or whatever you live, and you forgot to update the shipping address for something? And that's what happened to me a couple of weeks ago. I accidentally ordered one thing to the previous address, and I had to, today had to go to that was actually a hotel, and the stuff that can give me the package was working only like 1 hour in the morning. So I finally managed to take the package back. But yeah, enough of the cool but not cool stories. So again, let's take a look. I think so in the mathematics there are two ways to show the problem: numerical and analytical. Numerical we recently took a look, and right now we will go for the analytical. I think to compute the derivative of functions using the analytical method, we can split them into simple elemental functions, finding the derivative of those, and then applying the chain rule, which we will explain soon, to get full derivative. So basically, and since the neural network is you can refer to it as a very complex function that consists of the subfunctions, and I think the idea that we'll calculate the derivative for these subfunctions, and then using this chain rule we'll calculate the final one. To start building an intuition, and start with the simple functions and their respective derivatives. Maybe I can do this. Yes? Yeah. While we're reading. The derivative of simple constant function. There is a function that takes argument x and returns the same value. Well, basically it doesn't need an input. And if we calculate the d by, I'm not sure how it's probably how to properly read it in English actually. D by dx from the f from x is, well, d by dx. You can correct me if I'm reading it incorrectly. I really don't know how to properly read it in English words. But the difference here is the zero. I mean, for the small change you have the same number, so the actual difference is the derivative of a constant function, calculation steps. Let's take a look. Okay. It's not that big difference. When calculating the derivative of a function, recall that the derivative can be interpreted as a slope. In this example, the result of this function is horizontal line, as the output value of any x is 1. So basically we have the horizontal line. So I guess the, well, horizontal meaning that it's has 90 degrees angle onto y. By looking at it, it becomes evident that the derivative equals 0 since there is no change from one value of x to any other value of x. So there is no slope. I mean, because the line is horizontal. So that's, you know, like, okay, def x, f from x, and it return 1, right? So then we be array then y equal to f from x, and then plot x, y. No, what did I miss? X, y. Okay, I will not dive into this. So basically, it should be a straight line here, but oh, yes, because of this. And, yeah, so right now, okay, right now I want to. Oh yeah, because yeah, that's the trick to convert it into array. So basically, there is a straight line parallel to the x-axis, and there is no slope. I mean, there is no, for example, crossing with the x. It means that there is no, like, you know, angle that you can check between the x values and the actual function line. So basically there is, and with the change of the x value, there is no change in the output, right? So the derivative of the slope is 0. Okay. So far we are calculating derivatives of the function by taking a single parameter x in our case. In each example, this changes with partial derivatives, since they take functions with multiple parameters, and will be calculating the derivative with respect to only one of them at a time. And now with derivatives, it's always with respect to a single parameter. To denote the derivative, we can use prime notation, where for the function f from x, we add the prime, like f prime from x. For our example, f from x equals 1, the derivative f prime from x is equals 0. Another notation we can use is called the Leibniz notation. The difference on the prime notation with multiple ways of writing the derivative with the Leibniz notation is as follows. Yeah, I get used to this notation. df from x divided by dx. Or this one. Each of this notation had the same meaning, the derivative of a function with respect to x. So we have the input one, and the function. In the following examples, we use both. In the, okay. Where is it? In the following examples, we'll use both notations, since sometimes it's convenient to use one notation or another. We can also use both of them in a single equation. In the summary, the derivative of a constant function equals 0, because there is no change. I mean, it's constant, right? So how it would change anything the derivative of the linear function. So we have the function that is linear. So we have the change So we have the x value 1 and we have the function value 1. Yeah, any value in the 0 power is always equals to 1. The derivative of the linear function calculation steps. In this case, the derivative is 1, and the intuition behind this is that for every change of x, y changes by the same amount. So y changes 1 times the x. 1 times the x. Derivative of the linear function equals to 1, but not in every case. We'll explain next. Yeah, I guess, yeah, if you have a constant, that's what you will have this multiplier always. So for example, yeah, this is, we have the remaining 2, and then there is, we can move this constant out this equation, and then you have the same as the previous one. And yeah, usually, I mean, the derivative of the linear function is the k value before the x. Well, not the usual, it's like this. When calculating the derivative, we can take any constant that the function is multiplied by and move it outside of the derivative. In this case, it's 2 multiplied by the derivative of x. Since we already determined that the derivative of linear function is 1, we now multiply it by 2 to give us the result. The derivative of the linear function equals the slope m. In this case, m equal to, so okay, we use m. Remember that was k. If you associate this with numerical differentiation, you're absolutely right. We already concluded that the derivative of a linear function equals slope. In this case, is a constant, no different than the value 2, and it's not a parameter. Every non-parameter to the function can't change its value, those we consider it to be a constant. We have just found a simple way to calculate the derivative of a linear function and also generalized it for the equations of the different slope m. It's also an exact derivative, not an approximation as with the numerical. What happens when we introduce exponent? I mean, they show in the calculation step, but they don't. Well, maybe it will be next, but for example, why it's -1? I mean, yeah, it's the rule that if you have the power, then you need to take the constant from the power, move it as a multiplier before, and then subtract 1. So for example, if it's x in power of 2, then the derivative will be 2x. If it's x in power of 3, that will be 3 multiplied by x in power of 2. Yeah, maybe it will be. First, we apply the rule of constant. We can move the coefficient, the values that multiply that outside of the derivative. Okay. The rule for handling exponents is as follows. Take the exponent in case of 2 and use it as a coefficient for derivative value, then subtract 1 from the exponent. I mean, yes, from the math it's like this, but probably it's like you just have to, take it as a fact, at least from this book, because I don't remember how it was described. Well, when you study the derivatives as a math topic, and I don't remember, to be honest. But I remember that these rules, how to take the derivative. I mean, how they called alpha. Not numeric. How it's called? Okay, the proper derivative. Yeah. Where is it? If it's this means the slope of the tangent line at any point x for this quadratic function will be 6 multiplied by x. As discussed with the numerical solution of the quadratic function differentiation, the derivative of a quadratic function depends on x, and in that case it equals 6 multiplied by x. So yeah, so we remember this the quadratic one. So based on since it's not the linear, based on the x value, the slope, I mean the angle that this tangent line and the x line creates will be different. So the higher the value, the more angle will be, and the value will be bigger. Commonly used operator in functions addition. How we do calculate the derivative in this case? Well, the derivative from the sum, it's the sum of the derivatives, right? So yeah, so we have 6 multiplied by x plus 5. So this is the derivative for the for such a complex function. Actually, can we? Do they have? No, I want to represent this one. So it's it's 3 multiplied by x and plus 5 multiplied by x, right? Okay, so we have, for example, value 1, and it's 8. Should be 8, right? Okay, for example, we have 2, 4, 12. Yeah, okay. Yeah, but it's still quadratic. You know, the shape is quadratic. For example, it's 0, 10. What's this? No? Oh, and always forgets. Yeah, it's just the actual values are different, and it's a little bit, stretched because you're adding another function to this. So yeah. So yeah, derivative from the sum of the two functions, it's the sum of the derivatives, and then we calculate each derivative, and then we have the linear function that represents the slope for this one. So if we will draw the slope for each value, for example, it will be like here, 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 and so on. Derivative of the sum operation. The sum of the derivatives we can apply. Can split the derivative of a more complex sum operation into sum of the derivatives of each term of the equation and solve the rest of the derivatives using the method we already know. The derivative of a sum of the functions equals the derivative of a sum of function equals the derivative. Well, this is just a proper notation. In this case, we have shown the rule using both notation. Let's try a couple more examples. Okay, we're 25x in power of 4 plus 12 multiplied by x in power of 2. That's it. Yeah, and we remember that the derivative from the constant is 0. So minus 0. Okay. Yeah, looks like I still remember something from my math. The derivative of a constant 5 equals 0, as we already discussed in the beginning. Okay, so this looks relatively straightforward so far, but with neural networks we will work with a function that take multiple parameters as an input. So we're going to calculate the partial derivatives as well. Okay, let's summarize some of the solutions and rules that we learned in this chapter. The derivative of a constant equals 0. By the way, the first the first derivative shows the speed of speed of change of the function. The second derivative shows the acceleration, so you can calculate how fast changes. I mean, with the first one you can calculate how fast, if I remember correctly. Yeah, so you can calculate how fast the changes. The more you increase the x, how fast the increases the value. With the second derivative you can calculate the acceleration, so how fast the speed of change changes. And of course you can, and what is the second derivative? You take the first one and then you take another derivative from the third derivative. So for example, for the linear function, the second derivative will be 0. Yes, because the first derivative is a constant value, the second one will be 0. But for example, for quadratic function, the first derivative is the straight line, well, is the linear function, then the second derivative will be constant. Derivative of a linear function equals its slope. The rules: derivative of a constant multiple of the function, the constant multiple. No. The derivative of a constant multiple of the function. Okay, so yeah. Oh, the... okay. The derivative of an exponentiation. Yeah, so we take this, so we have the power value, we use it the constant, and then we subtract 1 from the... It actually wasn't that clear, for example, when they explained why the derivative from the linear function equals constant. So for example, for example, if you don't know this rule, that it's not clear, and it took me, off guard until I remembered this one. So I would say that it should be explained even before discussing the derivative of a linear function. It just, those things just makes more sense, because it first is explained when we have a quadratic function, and then you can understand it better. So, but apart from this, I think the explanation is really good. And there is a multiplication, and then there is a sum. Yeah. Chapter code for the resources. Interesting what they want to show with the chapter code. Nothing here yet. Okay, chapter 8. I recorded around half of an hour, but I will cut a little bit. So let's continue. I think as I checked in the previous one, I think this one and this one chapters will be mostly about the math, without too much coding. So because there is a partial derivative, well, maybe I will write something with the Python, but it looks like there's a gradient, the chain rule. Oh, there is some code, so maybe we'll actually write something, but it's rather short chapter, so I will try to go through this chapter right now, so tomorrow we will continue with the coding, because how long you can learn the practice, or how long you can learn some things without coding. It's stuff. Two of the last pieces of the puzzle before we continue coding. Before we can continue coding our neural network are the related concept of the gradients and the partial derivatives. The derivatives that we have solved so far have been cases where there's only one independent variable in the function. So the result purely depends on the x value. However, our neural network consists, for example, of neurons which have multiple inputs. Each input gets multiplied by this corresponding value, a function of two parameters. Okay, so it's something like, it's like m multiplied by x plus b, something like that. Yeah. And we'll explain soon in details to learn the impact of all of the inputs, weights, and biases to the neuron output at the end of the last function. We need to calculate the derivative of each operation performed during the forward path in the neuron and the whole model. To do this and get the answer, you'll need to use a chain rule, which we'll explain soon in this chapter. Okay, the partial derivative. The partial derivative means how much impact a single input has on function's output. The method for calculating the partial derivative is the same as for the derivative explained in the previous chapter. We simply have to repeat this process for each of independent inputs. Okay. Each of the function's input has some impact on this function's output, even the impact is 0. We need to know this impact. This means that we have to calculate the derivative with respect to each input separately to learn about each of them. So, I read it like this. In some cases, for some outputs, some neurons has 0 impact, but for another input, it could have a drastic impact. For example, in the model that we're building right now, there are 3 groups of the data, and our model tries to predict the class based on the input. And probably for the first class, there will be one set of the neurons that gets more activated and has higher impact. For the second class, there will be another set of the neurons that has more impact, and the previous one will have less impact. And I think that's the goal of this. That's why we call this partial derivative with respect to given input. We are calculating the partial of the derivative relative to a single input. The partial derivative is a single equation, and the full multivariate functions derivative consists of a set of equation called the gradient. In other words, the gradient is a vector of a size of inputs. For example, I had the 100 inputs, so this will be the gradient size of the 100, containing partial derivative solution with respect to each input. We'll get back to gradient shortly. Did you note the partial derivatives will be using Euler's notation? It's very similar to Leibniz notation, as we only need to replace the different operator D with while the operator D might be used to denote the differentiation of multivariate function, its meaning is a bit different. It can mean the rate of functions change in relation to the given output, but when other inputs might change as well, and it's used mostly in physics. We're interested in partial derivatives, a situation where we try to find the impact of a given input to the output while treating all of the other inputs as constant. We're interested in the impact on the singular input since our goal in the model is to obey the parameters. how this symbol is called. So is around the D called version. Okay. The partial derivative of a sum. Calculating the partial derivative with respect to a given input means to calculate it like the regular derivative of one input, just while treating other inputs as constant. Okay, so for example, we have a function that depends on two variables, x and y. So we want to calculate the derivative from it, so we have the... so we calculate in two different derivatives. For example, one for the x, so we assume in this case that everything with the y is a constant, so it will produce a 0, and vice versa. So for example, in this case, there is a derivative by x and derivative by y. In both cases it's constant, but in the first case this constant comes from the x part of the equation, and the second part it comes from y part. First we apply the sum rule. The derivative of a sum is the sum of derivatives. Then we already know that the derivative of x with respect to x equals 1. The new thing is the derivative of the y with respect to x. As we mentioned, y is treated as a constant, as it does not change when we are deriving with respect to x, and the derivative of a constant equals 0. In the second case, that is switched. This will not always be the case, though as we will see. For example, we have another example that's better. So we have 2x, so we have the linear and the quadratic function, and then we calculate in the first with respect to the x. So that should be 0, right? So, okay, so we're taking the derivative as usual, but then we replace the y with the 0. Actually, okay. So there is 2x. So there is 2. Okay. So this is the linear, so the derivative will be constant value. And here we should treat it as the y we should treat as 0. So so even if it's in the power of 2, that still will be a constant, and the derivative of a constant value so we're trying to take the derivative by x from the y, which gives us 0, and vice versa. So that should be 0, that should be 3 multiplied by 2 multiplied by y, so that's 6y. This example we applied the sum rule first, then moved constants to the outside of the derivatives and calculated what remained with respect to x and y individually. The only difference to the non-multivariate derivatives from the previous chapter is the partial part, which means we are deriving with respect to each other of the variables respectively. Other than that, there is nothing new here. Let's try something seemingly more complicated. So we have x, y, x, and well, that will be 0. So if we take the derivative by x, that should be 0. That will be 9 multiplied by x in power of 2 plus 5. Okay. If we take the derivative from this one by the y, that should be minus 2 multiplied by y. Okay. Pretty straightforward. We are constantly applying the same rules over and over again, and we did not add any calculation or rules in this example. The partial derivative of multiplication. That will be the interesting one, right? So we have for example, we have a function that is not a sum, but the multiplication of the inputs in it, and that's actually what will be in our neural network, right? We have already mentioned that we need to treat the other independent variables as constant, and we also have learned that we can move constants to the outside of the derivative. So if we assume that y is a constant, then we can move it outside, take the derivative from the rest. So it will be like a, okay. It turns out that we need to derive with respect to x and y is treated as a constant, as a result equals 1 multiplied by, which is 1. The whole derivative then results into y. The intuition behind this example is when calculating the partial derivative with respect to x, every change of x by 1 changes the function's output by y. That's true. For example, if y equals 3 and x equals to 1, the result is 3, but if we change x by 1, then the overall change will be 1 multiplied by 3, which is the y value, right? So this is, yeah. Let's introduce the third input variable and add multiplication of the variables for another example. So we have it's okay. If we're taking the derivative by x, that means that everything else is the constant value. I mean, 2 other y and z. So in this case, we will have 9 multiplied by z multiplied by x in power of 2, right? In this case, that should be 0, because that's the constant. In this case, that will be 5 multiplied by the derivative from z by x, which will be 0. And we don't have x here, so that will be 0. So, okay. For the y, that will be 0. That will be minus 2 multiplied by y plus 2z. Okay. And by that, it will be 3 multiplied by x in power of 3. That will be 0, that will be 5, and that will be 2 multiplied by y. The only operation here, as mentioned, moving variables other than the one that we derive with respect to outside of the derivative. The result in this example appears more complicated, but only because of this existence of other variables in them. I mean, I'm feeling like I'm in university again. I mean, I didn't have to, well, not in university, but, actually, solving the math equations. It's not happening that often, really. But maybe, oh no, actually, I had it I think last year too. So yeah, no, it's not true. The reason to run about partial derivatives is that we'll be calculating the partial derivative of multivariate function soon, an example of which is neuron. From the code perspective and the dense layer class, more specifically the forward method of this class, we are parsing in a single variable, the input array containing each either a batch of samples or outputs from the previous layer. From the math perspective, each value of this single variable is a separate input. It contains as many inputs as we have data in the input array. For example, if we pass a factor of 4 values to neuron, it's a singular variable in the code, but 4 separate inputs in the equation. So we have 4 different variables, right? This form of function takes multiple inputs to learn about the impact that each input, like each node input, makes to the function's output. We'll need to calculate the partial derivative of this function with respect to each of its inputs, which we'll explain in details in the next chapter. Partial derivative of max. So the gradient. Okay. So there is a partial derivative of max and the gradient, the chain rule, and yeah, I think this is in the summary. So there are actually a couple of things, and I don't want to jump over the things and just quickly skip through these chapters. I want to remember in this and kind of put it, well, first read it, sleep with this, read it, sleep with this, because I think the next couple of chapters will be implementing the things that we learn in these 2 chapters. So I'm leaving this half of this chapter for tomorrow. I don't want to really, speed it up, but I think I will finish this part of the chapter maybe like tomorrow in maybe 20 minutes, and then we will get back to the coding. But for now, what do I want to say? But for now, if you're still here, you're watching this part of the video, you can mention about this in the comments. I will be very glad if you tell me that you enjoyed these videos somehow. And don't forget to check my main channel where I do talk about things around tech and stuff. But for now, I see you tomorrow. Bye bye.